Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Simpson's Rule with and without incorrection. A line is not well suited to approximate a curve in a large interval. The approximation error, gap between the curve and the line, can be very large. However, a parabola, as an interpolating function, may be used to reduce this gap, but fitting a curve with a unique parabola requires 3 data points, or 2 panels. The fitting of 3 points to a parabola, centered about x1, can be expressed as follows. Now, integrating the parabola on the interval from x0 to x2 yields the following approximation for the area under the curve. This approximation is called the Simpson's rule or Simpson's 1/3 rule due to the 1/3 factor. To improve the accuracy of the numerical integration, we double the number of panels and integrate over the interval from x0 to x4. Using the first 2 panels, we integrate the resulting quadratic polynomial P2(1x) between x0 and x2 to get the area A1. Likewise, using the last 2 panels, we integrate P2(2x) over x2 to x4 to find the area A3. We then apply the Simpson's rule to the A1 and A3. After simplifying, we get the following expression. A generalized approximation for multiple panels is obtained as follows. This formulation is called the in-panel or composite Simpson's rule. The global or truncation error term is given by the following expression. An improved Simpson's formula can be found by constructing a 4th-degree polynomial approximation, which passes through the points A, B, and C. 2 more points are generated using the derivatives at the interval endpoints. Hence, we have the following system of linear equations, with 5 unknowns, A1 through A5, which are solved. Integrating the polynomial P4x over the 2 panels, from x0 to x2, yields the following expression. Generalizing it for n panels leads to the composite formula. The correction term here is analogous to the trapezoidal rule with incorrection, so we refer to it as Simpson's rule with incorrection. Another version of Simpson's rule can be obtained with 3 panels. A cubic interpolating polynomial passing through all 4 points is constructed and then integrated over the interval from x0 to x3 to give the following expression. For the composite rule, we can generalize the 3-panel rule to give the following. Due to the 3 of 8 multiplier, this formula is referred to as Simpson's 3 of 8 rule. The total number of panels in the 3 of 8 rule should be in multiples of 3. In practice, when n is even, the 1/3 rule is preferred due to its smaller global error. When n is odd, the Simpson's 3 of 8 rule is only applied to the last 3 panels, while the 1/3 rule is employed for the rest. The advantages of Simpson's rule are: Simpson's rule is relatively simple and easy to employ. Due to being 4th and 6th order accurate methods, the Sn and Csn yield the true integral values for polynomials of degree m less than or equal to 3 and m less than or equal to 5, respectively. Error analysis is straightforward. The disadvantages of the Simpson's rule are: integrands must be continuous. The number of panels is restricted to even numbers for the 1/3 rule and multiples of 3 for the 3/8 rule. The formula with the incorrection cannot be applied to discrete functions unless the first derivatives are computed using a high-order finite difference formula. Even though Simpson's 1/3 rule has a 4th-order error, it may not always be superior to the trapezoidal rule. The global errors for the trapezoidal and Simpson's rules depend on the second and fourth derivatives, respectively. In cases where the integrand is not smooth, higher derivatives and hence the truncation error may become very large. That is why you should make sure that the integrand is sufficiently smooth before applying end-correction formulas. Otherwise, there may be little or no advantage at all in using a so-called better rule. Let us consider evaluating the following integral using the composite Simpson's rule with uniformly spaced n equals 4 and 5 panels. We will repeat the numerical integration using the composite Simpson's rule with n correction and estimate the theoretical upper bound of the numerical error for S4. The true integral is natural logarithm 2. For n equals 4, we construct and tabulate the abscissas and the ordinates. The Simpson's 1/3 rule can be considered as a weighted sum of fxi's. The weights placed in the fourth column are 1 for the first and last row, 4 for the odd-numbered rows, and 2 for the even-numbered rows. The fifth column is the product of the functions and corresponding weights. The sum of the last column gives the term of S4 in parentheses, which yields 0.693254. To estimate the integral with n-correction formula, we need to find the sum of the encircled term as well as the first derivatives of the endpoints at the correction term. Note that the weights are 7 for the first and last rows, 16 and 14 for the odd and even-numbered rows, respectively. The last column's sum yields the value that corresponds to the encircled term. The first derivative is minus 1 over 1 plus x squared in parentheses. Then f'1 minus f'0 is found to be 3 over 4. Substituting 3 over 4 in the 4-panel Simpson's formula with n correction, we obtain 0.693144. 4h equals 0.2. We calculate and tabulate xi and fi's with subscripts starting from 0. The weights of Simpson's 1/3 rule are 1 for the first and last rows, 4 for the second and fourth rows, and 2 for the third and fifth rows. The sum of the fifth column yields 9.873016. Substituting this into the 5-panel Simpson's formula, we get 0.6582011. The weights of Simpson's rule with n correction are 7 for the first and last rows, 16 for the second and fourth rows, and 14 for the third and fifth rows. The sum of the fifth column yields 51.611111. Recall previously we had already found the first derivative and its values at the endpoints. Substituting the sum of the fifth column along with 3 over 4, we obtain 0.6851,481 as the estimate of CS5. Note that we have deliberately implemented Simpson's 1/3 rule for a 5-panel numerical integration problem, even though we shouldn't have. Since Simpson's 1/3 rule with and without n correction was derived for an even number of panels, what we did was wrong and will lead to erroneous results to some extent. If we are going to integrate an explicitly given function, we always opt for an even number of panels, as we have the freedom to predetermine the number of panels. However, if we have a discrete dataset consisting of an odd number of panels, then the Simpson's 3 of 8 rule can be applied to the last 3 panels, while the 1/3 rule is for the rest. Now, to carry out the numerical integration in this way, we will apply the Simpson's 1/3 rule to the first 2 panels and the 3 of 8 rule to the last 3 panels. Here, h is the panel width. Performing calculations, we find 0.6932044. Comparing the numerical estimates, we find that the true error of the estimate with 4-panel Simpson's rule, S4, is minus 1.067 times 10 to the minus 4. The true error of the Simpson's rule with incorrection, CS4, becomes 2.347 times 10 to the minus 6, about 50 times smaller. The 5-panel Simpson's rule with and without the incorrection, S5 and CS5, yield much larger errors. It is not surprising to see that these formulas led to larger errors, as they were not intended for an odd number of panels. When we apply the 1/3 rule to the first two and the 3/8 rule to the last 3 panels, we obtain a result with an accuracy between S4 and CS4. When we have an explicitly given function, we can predict the upper bound of the error for a given number of panels before carrying out the actual numerical integration. To calculate the global error R4, we need the value of the fourth derivative of the function fx at x equals xc. Let us consider the error term of the S4. Note that xc is unknown here. To find the upper bound, we can replace the derivative term with its maximum magnitude. We note that the fourth derivative of f is a decreasing function whose absolute maximum value of 24 is at x equals 0. Substituting this value into R4, we find the upper bound of error to be 5.21 times 10 to the minus 4, which is, as expected, greater than the true error for S4. With this note, we end this session. That is all for now. See you next time with another topic. Bye.